Hello everyone, I'm Zhonghen Tang, a PhD student from Beihang University, currently interning at Baidu. Today I will introduce our paper, DETR with additional global aggregation for cross-domain weakly supervised object detection. We propose DETR with additional global aggregation, named DETR-GA, a cross-domain weakly supervised object detection, named CDWSOD detector, that simultaneously makes instance level plus image level predictions and utilizes strong and weak supervisions. The key point of the DETR-GA is very simple. For the encoder and decoder, we respectively add multiple class queries and a foreground query to aggregate the semantics into image-level predictions. Extensive experience on 4 popular cross-domain benchmarks show that DETR-GA significantly improves CDWSOD and advances the state-of-the-art. Our task is CDWSOD. First, let's introduce domain adaptation, which can be divided into 3 categories. Unsupervised, only knowing whether the images are from the target domain or source domain with limited adaptation effect. The supervised, having complete annotation information with better effectiveness but higher annotation costs. The weakly supervised, having classification labels for the images but not the bounding box, with the advantage of achieving a good trade-off between the adaptation effect and the annotation cost. CDWSOD requires using weak supervision on target domain to transfer the knowledge from the source domain. Therefore, it is essential to supplement the detector with image-level prediction capability. While in DETR, the encoder and decoder complements based on the attention method and thus have strong capability to capture long-range dependencies, which is favorable for aggregating semantic information to make image-level predictions. Thus, for the encoder and decoder, we respectively add multiple class queries, a foreground query to aggregate the semantic information across the entire image. The key point of DETR-GA is the newly added class queries and foreground queries in the encoder and decoder, which promises the global aggregation for image-level predictions. For example, we visualize the attention maps of the class query and the foreground query. Although there is no precision supervision for the bounding box, we can see that the green person class query can still focus on the global positions of the persons, while the blue dog query only focuses on the position of the dog. The response target of the foreground query covers all the foreground regions, and we can see that it responds to the people, dogs, and even the trees that may be the foreground targets. Overview of the proposed DETR-GA. DETR-GA tries to transfer the detection knowledge from the fully labeled source domain S to the target domain T through weak supervision, based on a DETR-style detector consisting of the backbone, encoder, and decoder. DETR-GA adds 2 modules. For example, the class query and the foreground query. In the encoder, multiple class queries aggregate the class-specific information from all the feature tokens through cross-attention. In the decoder, the foreground query and the object queries are correlated with each other because they share most processing except that the foreground query has no position embeddings. Correspondingly, they make image level and instance level predictions respectively. Overall, we utilize the weak supervision hybrid, for example, the weak and strong supervision for the encoder and decoder, therefore aligning the class semantics between the source and the target domain. The class query queue consists of C nullable queries. C is the number of the categories. The cross-attention between the class query queue and the image patch T is used to aggregate category-related information. The output of each class query is used to perform binary classification to predict whether the category exists in the image. We use a foreground query for global semantic aggregation. Removing the position embedding encourages the foreground query to focus on the semantic content for global information aggregation. Sharing the decoder parameters This correlation encourages the foreground query and the object queries to share concerns on the class semantics, and thus benefits class-wise elements. Both the class query loss and the foreground query loss are binary cross-entropy loss. We follow some common practice on the backbone to add an adversary loss and for domain-level alignment and an image-level classification loss. The overall loss is divided into three parts: the backbone, encoder, and decoder. During inference, DETR does not need the image-level predictions and thus resumes the standard pipeline without extra computation cost. We showed the results of the domain adaptation from Pascal VOC to clip-part dataset. It can be seen that compared to the previous sorter methods, we improved by nearly 10 points on clip-part all, and by around 4 points on clip-part test. Above are our results on the domain transfer from Pascal VOC to the comic and watercolor datasets. The bottom left shows the improvement compared to the best CNN method in the domain. The source-only method is trained on the source dataset and tested on the target dataset. We can see that using the DETR-like detector alone does not bring advantages in the source-only case. However, after using our DETR-GA, we can achieve more improvement. For example, the original best CNN method can bring a 40-point improvement on clip-part all, while we can directly bring a 50-point improvement in MAP. The left figure shows the ablation results of each component separately, where the baseline corresponds to the alignment on the backbone. We can see that each part can bring significant improvement, among which the improvements brought by the class query and the foreground query are most significant. Moreover, combining class query and the foreground query can bring more improvement. The right figure compares the method of using class query with the method of directly proving the output tokens of the encoder and performing multi-classification. We can see that directly performing global classification at the encoder also has some improvement, but the effect is not as significant as using the class query method. The left figure shows the ablation experience on the foreground query. We can see that not sharing weights with the object query and adding precision embeddings both reduce the effectiveness of the foreground query. The right figure shows some visualizations of the foreground query, the response level to the patch tokens in the encoder. That's all. Thank you.